All right, so welcome to the Morrison Planetarium. My name is Mary. I'm going to be your presenter today. I'm in the pilot's booth at the top of the room up here, waving my arms. Hello, everyone. Welcome. And today you're here to see Tour of the Universe, which is one of my favorite shows to give that we have right now. Most of the shows that we have throughout the day are mostly pre-recorded, movies kind of, with a short section where I can tell you about some update to the astronomy that we see in the show. This show is a bit different. This is a completely live show, so I'm going to be live flying us through the universe today. And we'll start out at Earth, and we'll see how far out in space we can go in the next 25 or so minutes here. We are starting our tour of the universe today relatively close to home, just a few hundred miles above the Earth's surface at the International Space Station. And I always like to start us out at the International Space Station to give us a little bit of perspective of what we're going to be seeing today. Because today we are going to be covering incredible distances. We're going to see how far any of our human influence has gone out into space. So things like how far do humans travel out into space? How far have we traveled in the past? How far have our spacecrafts gone? And we're going to go even farther than all of that. But the International Space Station, like I said, just a few hundred miles above the Earth's surface, is as far as humans travel out into space right now. You can fit about 6 or so astronauts on the ISS at any one point. And the longest that any one particular person has lived there is about a year or so. In general, we've had people up there for about 20 years now. And they're traveling very quickly around our planet. I'll turn on the orbit here so you can see where the orbit of the International Space Station is in yellow, or kind of orange, I guess. And they're traveling very quickly. Only takes them about 90 minutes to orbit us once. But this is how far we go right now, just a little bit above our planet. And as I zoom out, we'll start to see some more features on the Earth, and everything we'll see today is actual pictures or data based on observations that we have made out there in the universe. So I'm using our OpenSpace software today, which is a free open source planetarium software. So when you go home today, if you're interested, you can look up OpenSpace project and you can actually download this for free at home if you want. But the cool thing about OpenSpace is that it uses all real up-to-date data. So all these clouds that we're seeing on the Earth, this is the actual map of where these clouds were. I think they update it like 3 a.m. every day or something like that. So this is where these clouds were today and where the International Space Station is right now. But I'm going to keep us zooming away from our planet because we have a really long way to go. So I want to make sure we can get to everything as we go out into space. But our next stop as we zoom away from the Earth is our closest natural neighbor. I say natural neighbor to distinguish it from any of our human-made neighbors that we have going around our planet. We have a lot of satellites that we have created and are orbiting around the Earth. But we're going to go over to our natural satellite, the Moon. Ooh, and that was kind of quick. Sorry about that. But we're going to fly over to the Moon, which is as far as humans have traveled out into space so far. The Apollo astronauts came out here back in the 60s and 70s, a little over 50 years ago now. But that's as far as our human footprints have gone, is our closest natural neighbor out here, about 250,000 miles away. And at the Moon is where I like to introduce a new idea, because the distances that we're going to cover today, if we use miles and kilometers, already we're up to 250,000 miles just going to the Moon. So the numbers are so large that it starts to be difficult to really grasp what that means if we use miles and kilometers. So from here on out, we're going to imagine that we are traveling at or faster than the speed of light, which is the fastest speed we know of. So if we were traveling at the speed of light, it would take us about 1.5 seconds to get to the Moon from Earth. So about the amount of time it took us flying in open space here. And so that's a new distance that we're going to use, is light speed. So we say that the Moon is a distance of 1.5 light seconds from Earth, because that's how much time it would take if light was actually traveling from Earth to the Moon. And before we fly away, I am zooming us in a little bit on the Moon because it's just really gorgeous. I really like these high-resolution images that we have of the moon's surface. From some of the spacecraft that we've sent out here, we do have spacecraft that orbit the moon and take these lovely pictures for us. And if we zoom away from the moon, I'm going to bring up some more orbit lines here. So we saw that kind of yellowish orange line before to show us the orbit of the International Space Station. From now on, we're going to have some blue lines up that are going to show us where the orbits of the moon and also the planets in our solar system are. And I'm going to focus for a moment on the center of our solar system, the closest star to us, the sun. So the moon, our closest neighbor, 1.5 light seconds away from us, not too much time to get there if we were traveling at the speed of light. If we're talking about the sun, now we're up to light minutes of distance already. So if we were to travel from Earth to the sun, traveling at the speed of light, that would take us about 8.5 minutes. So another way to think of that is that if the sun just disappeared for some reason, we wouldn't know about it for 8.5 minutes. But don't worry, the sun isn't just going to disappear. There's no reason why that would happen. Or if you walk outside and you look at the sun, first of all, don't look at the sun. But if you did, that is what the sun looked like 8.5 minutes ago, not what it looks like right now. And the closer orbits we're seeing are Mercury, Venus, Earth, and Mars. And there's a pretty sizable gap in between Mars and Jupiter, but that's not totally empty space. That's where most of the asteroids are in our solar system. Not all the asteroids, but most of the asteroids orbit in between Mars and Jupiter in what we call the asteroid belt. So rocky objects in our solar system. But beyond the asteroid belt, now we're seeing the orbits of Jupiter, Saturn, and then we'll see Uranus and Neptune. And already, we're still in our solar system. We haven't gone super far in terms of all the things that we can see out there in the universe, but we're already up to light hours of distance now. This is where I like to bring up the orbit of my favorite dwarf planet, Pluto, because if we were to travel from one end of Pluto's orbit to the other, it would take us roughly 9 hours or so. So we've gone from 1.5 seconds to the closest neighbor, the moon, farthest humans have traveled, 8.5 minutes to get to the sun, and now several hours to travel across a good portion of our solar system here. And I also like to give a quick side note whenever I'm out here at Pluto, because to this day, one of the most common questions I get as a person that works in astronomy and works in the planetarium is, what's up with Pluto? Why is Pluto not a planet anymore? Why do you hate Pluto? Well, I'm here to tell you, I don't hate Pluto. I actually quite like Pluto. But the main reason that we don't call Pluto a planet and why we call it a dwarf planet has to do with where it orbits. So I'm going to bring up a bunch of trails here. It's going to look kind of bright, just a warning. There we go. And these are showing us trans-Neptunian objects. So basically objects that orbit outside of the orbit of Neptune. And some of these have some really wild, long orbits that come in closer to the sun and go really, really, really far out. But you can see that a lot of them, they're kind of in this almost ring or belt, sort of, kind of similar to the asteroid belt, but just farther out. So that's what we call the Kuiper belt, is this area of lots of small, mostly icy objects, some rocky objects out far out in the solar system. And Pluto goes right through that, which we did not know until the late 90s and early 2000s when we started to find all these other small objects out here, and several objects that were around the size of Pluto. So the decision was made back in 2006 by a group of astronomers that we needed to come up with a new category because there were several smaller objects like Pluto that maybe should be planets, but also had all this stuff in their orbits. And they decided that one of the requirements for a planet was it needs a clear orbit, it needs to have cleared out its path. Pluto did not fulfill that requirement, so it was changed to a dwarf planet. But still a very interesting place, and one of the only places in our solar system where we have specifically sent a spacecraft nearby to take wonderful, beautiful close-up images. So we have some really nice images of Pluto. And that brings me to this next thing that I brought up, which let me turn off the asteroid belt for a minute there. So these orange lines we're seeing here now, This is us checking in once again with our kind of human influence out here in space. So we saw how far humans travel right now, the ISS, how far humans have traveled in the past to the moon. But now we're seeing how far our spacecraft have traveled. So we've sent out a few spacecraft that we purposefully wanted to go outside of our solar system. They were traveling fast enough and going in the right direction that they'll leave our solar system behind. So these 5 are Pioneer 10 and 11, Voyager 1 and 2, and the New Horizons spacecraft, which flew past Pluto a few years ago and got us some lovely images. But even so, even with these ones, these are some of the fastest spacecraft we've sent out, and they've been traveling for a long time. The earliest of these, the Voyager spacecraft, they've been traveling since the 70s. Even so, they haven't quite gotten out to how far light could travel in a day. So we're still only out to light hours at this point. But we are getting to an area where it's a question of, are we still in the solar system or have we left the solar system? Because our sun has the 8 planets, it has dwarf planets, but there's a lot of other stuff that is influenced by the sun. The sun has a magnetic field. We think that maybe there's a bunch of comets orbiting around us really far away. There's asteroids all over the place. So it's a little tricky to figure out exactly where our solar system begins and where it ends. But if we get out to a few light years of distance, it'll be, without a question, outside of our solar system at that point. So we've seen the sun turn to its regular actual brightness. So before we were kind of dimming it down so you could see the things in the solar system a little bit better. But this is how bright the sun would be compared to the other stars that we see up in the sky. And if you look to your top left up there, you can see, and a little bit to the left, the bottom left as well, we are starting to fly past some of these other stars that you would see in the night sky. So if we're flying past other stars, we're definitely outside the solar system at that point. And now we're flying past stars that may have their own star systems, their own planets around them. And I'll show you where those are in just a moment here. But first, I want to make note of how far we've gone here. So to go across a big part of our solar system, or maybe even the whole solar system, that would take us at least 9 or 10 hours, probably less than a day for a lot of it. But if we were traveling at the speed of light and we wanted to get to the closest star outside of our solar system, that would take us 4 years. So space is very big. There's a lot of stuff out here. It'd take us a very long time even to get to the closest thing outside of our solar system. But around many of these stars that we're flying past and looking at, like I mentioned, a lot of them may have their own star systems, their own solar systems, so to speak, with their own planets. And I'm going to bring up some blue circles here to show us where those would be. So every single one of these is showing us a star that has at least one exoplanet around it. So a planet outside of our solar system. And we're finding these objects all the time. The first exoplanet that we confirmed was in the mid-90s. So we've been finding exoplanets for about 25 years. And we've already found over 4,000 of them. And just as many are what we call exoplanet candidates, where we think it's an exoplanet, but we need to watch it for a bit longer to confirm that it is, in fact, an exoplanet going around another star. And it's roughly around here where I do want to bring up our last bit of human influence out there in the universe, because there's something else that we're sending out into space beyond our spacecraft and how far we have physically gone ourselves, and that is the radiosphere. So this grid sphere that I put up here is to show us how far any of our signals could have gone. So things like radio signals. If those radio transmissions that we've sent out, if they're strong enough to escape our planet, they're all leaving at the speed of light and traveling at the speed of light. And if they don't run into anything, they'll just keep on going at the speed of light. And the earliest ones that were sent out were around the 1930s or so. So this is roughly 90 light years away from the Earth in all directions. So all that we're going to see from here on out is not because we've sent something to observe that object. Everything else we're going to see from here on out is because we've seen light from that object come to us and go into our telescopes, and we're able to observe it that way. And I'm going to bring down the exoplanet markers, but I am going to leave up the radiosphere because I always like to leave that on, see how long we can spot it as we zoom away, because we still have quite a ways to go, even though we've already passed how far our human influence has gone out into space. And we've been seeing an actual map of where these stars are, these individual stars that we can observe with our telescopes or even naked eye without a telescope. But in a second, the model's going to kind of switch over here, and we're going to see a model of something that we haven't taken a picture of and we haven't been able to see out with our telescopes because we can't go out this far. But here, this is a model of our Milky Way Galaxy. So we don't have a picture of our own galaxy, unfortunately, because we can't go outside of it, but we are able to see other galaxies. We're able to see quite a lot of what is, in fact, in our galaxy from where we are. And based on that, piecing all that together, we can make models like this that give us a good idea of what our galaxy would look like if we could fly outside of it. And I'll give you a second to see if you can still spot the radiosphere. That little teeny tiny dot near the top there. That's where we are. Out here, we are getting to some mind-boggling distances, even using the speed of light. Out here, we're talking thousands of light years. If we were to travel from one side of our galaxy to the other, traveling at the speed of light, it would take us about 100,000 years. And this galaxy of ours has billions of stars. We think maybe a few 100 billion stars, and very possibly just as many exoplanets too. We expect there might be just as many exoplanets as there are stars. But again, we're not stopping here. We're going to keep on going. And as we zoom away from our Milky Way Galaxy, we're going to start to see a lot of other dots showing up. And at this distance, these dots are no longer those individual stars. These are individual galaxies with their own billions or sometimes trillions of stars. And the colors that you're seeing here, these are not actual colors of these galaxies, though I do think it would be very fun if it looked like cosmic Skittles out there in the universe. But these colors are color-coded based on different surveys, so things like what telescope was used to see these galaxies, or are they in a particular group of galaxies, things like that. So we've kind of color-coded them based on different factors. And this is an actual map. We are seeing these galaxies. These are what we've seen with our telescopes. We've mapped out where they are relative to us. And now we're covering distances. I would, let's see, at this point, I don't know exactly how far out we are now, but I would guess a few billion light years at this point. So we've gone from thousands of light years to billions of light years. And because this is an actual map, that means that it's going to look a little bit strange because all of this is from our perspective here on Earth. So right around here, you'll start to see kind of a strange shape that these galaxies seem to make. Let me get us a good angle here so you can see that. Looks sort of like a butterfly or a bow tie, or sometimes people have referred to it looking like pasta or something like that. Now, the universe is not shaped like a butterfly, just like it's not a bunch of cosmic Skittles out there in the universe, though I do think that would be fun. This shape we're seeing is because we've only mapped out so much and because we're in a galaxy. So we're in the Milky Way Galaxy, which has a lot of stuff in it, a lot of gas, dust, stars, planets, all sorts of things that are blocking our view depending on where we look. So if we were to look in the direction of these gaps we're seeing on the top left and bottom right, you wouldn't really be able to see through the Milky Way very well. So you wouldn't be able to map out the galaxies in those directions like you can in the other directions. So there are even more galaxies than this, and we think probably just as many galaxies as the directions we have mapped out, but we just haven't been able to map them quite yet. And even farther than that, we're starting to see objects that are even older than galaxies and earlier on in our universe. And I'll point that out as well, that when we're looking at these things really far out in the universe, we're kind of time traveling in a way, because it takes so long for the light of these objects to get to us that by the time we see them and we see the light of them in our telescopes, that's how they looked billions of years ago. So if you remember at the beginning of the show, I mentioned that if you look at the sun, which again, don't look at the sun, but if you were to look at the sun, that's how the sun looked 8 minutes ago, not how it looks right now. And this, what we're seeing, this map of the universe, this is what our universe was like billions of years ago, not what it looks like right now. And because of that, that means that there is only so far we can go. There's an edge to everything we can see in the entire universe. And that edge of our observable universe is the cosmic microwave background, the earliest light of the universe that we can see, which you won't see when you walk outside and look up at the sky tonight. But if you did have microwave vision, if you could see microwave light, you would see this every single place you look in the sky. But since this is kind of our limit here, the edge of our universe of what we can see anyway in the universe, that means that I can't take us any farther. So we're going to end our journey by flying back home, because I also don't want to leave you stranded out here in the middle of space. Now, as we fly back home, keep in mind, if we were really traveling at the speed of light, and if we were really this far away out in space, this journey would take us about 13.5 billion years. But thankfully, we're in the planetarium, so it should only take us about a minute or so. So here we go. And one last thought that I like to leave us with is that all of this that we've seen, all of these galaxies, planets, stars, dwarf planets, gas, dust, cosmic microwave background, all the stuff that we're looking at, we can see light from, that's not even everything we know to be in our universe. There are some really mysterious things out there, things like dark energy, which is some mysterious force that is causing our universe to accelerate as it expands. There's also dark matter, some mysterious substance. We're trying to figure out what it is, but we know that it doesn't interact with light in the way that we see with other objects. And we call these things dark energy and dark matter because we're not exactly sure what they are. But we do know that they make up about 96% of our universe. So all this that we've seen, this is only a teeny tiny portion of everything we know to be out there. Which I know can make folks feel kind of small and feel a little weird. And I agree, I feel that way sometimes too. But I also like to think of it as, well, sure, this is very large. I feel very small. We're this one teeny tiny dot in this gigantic universe. But look at all of this that we have found so far, just by looking through telescopes almost entirely. And there's a whole lot more to discover and a whole lot more to learn about. And I think that's pretty exciting. But still, I am always grateful when we're getting back into our little human realm of the universe as we re-enter the radiosphere. And we're going to head back on over towards that closest star to us, the sun. And we'll end our journey back at the third planet from the sun, where we've sent out all these spacecraft from, and all of our radio signals, and where all of us live. And the only place in all of this so far that we have found life at all, which is also pretty incredible to think about. And we're back home. Hooray! So with that, I want to thank you all for joining me today for our tour of the universe. I hope you enjoyed flying through space with me, and I hope you enjoy the rest of your evening. Thank you all so much for coming.